Catalysis is the process by which a catalyst changes the rate and mechanism of a chemical reaction. A catalyst is not consumed during the course of a reaction. In other words, it does its job and then it's available to do it again. Catalyzed and uncatalyzed reactions have completely different mechanisms. If we draw a capital letter E in a particular way, like so, over, down, over, and then cross in the middle, we draw a capital E. You might draw a capital E a different way. You might go down and then over, over, over. You get the same product, but it's a different mechanism. And that different mechanism is why catalyzed and uncatalyzed reactions have different activation energies. Whenever there's a different mechanism, some mechanisms are easier than others, and catalysts promote that. Homogeneous catalysts are present in the same phase as the reacting molecules. For example, enzymes, which are biological catalysts, are in aqueous solution, just like the substances in your body that enzymes work on are in aqueous solution. Aqueous solution for the enzyme, aqueous solution for the substances that are involved, therefore we have a homogeneous catalyst. A heterogeneous catalyst is one that exists in a different phase than the reacting molecules. Usually a solid catalyst in gaseous mixtures or liquid solutions. For example, in a catalytic converter in your car, the catalyst is often platinum, which is a solid, and the reacting molecules are gases. A catalytic converter has platinum as a heterogeneous catalyst. Research on catalysts is actually a very important area of modern science. If you're looking for something to do for the next 40 years, this might be something. The first step in catalysis is adsorption of the reactant molecules onto the active sites, or what I like to call the docking points on the catalyst molecules. After the reactants have adsorbed onto the active sites, the bonds in the reactants are broken or weakened enough that will allow them to break fairly easily, and this allows a lower activation energy in making the products. Then the products detach from the catalyst, and the catalyst is ready for more. As I mentioned on the previous slide, enzymes are biological catalysts. They are very large protein molecules, having atomic masses in the range of tens of thousands of AMUs up to millions of AMUs. They're very big molecules, very complex. They're folded and they have a very specific shape, which allows them to be really, really good at doing one thing, and that's it. So they're very specific. Typically, names of enzymes end with the suffix "ase." That's just a bit of trivia for you. Substrates, that's a term that's often used when we're talking about enzymes. When we use the word substrate, we mean reactants. Substrates are substances that react at the active sites of enzymes. The lock and key model explains how an enzyme affects a substrate molecule and changes it into a new substance. Let's look at this lock and key model. It's quite simple, really. There's a model of an enzyme, and there is a substrate molecule, or a reactant molecule. Mr. B, I thought you said enzymes were really complex molecules. That one looks pretty simple. Well, it's a model. That portion right there is the active site. And you can see that this enzyme is specifically shaped such that it's going to work very well with this substrate. What happens is that substrate fits right in there. Perfect. That combination we call the enzyme-substrate complex. The bonds in the substrate then are weakened or broken so that what happens next might be something like that. The products detach. They're not the same as in the reactant state. And there's the active site ready for more substrate. This enzyme will do its job over and over and over. The turnover number of an enzyme is the number of reactions it can facilitate per unit time. Enzymes in particular have a very wide range of turnover number, anywhere from thousands of reactions per second up to millions, tens of millions of reactions per second, which is frankly amazing. Enzymes can be put out of commission by enzyme inhibitors, which either bind to the active site or they alter the unique shape of an enzyme molecule, thus destroying the enzyme's activity. Here are a few examples of enzyme inhibitors: poisons, lead, mercury. Basically any type of toxin works often by screwing up your enzymes. And there are two ways that an inhibitor can screw up your enzymes. One is by binding to the active site, like that. You can see that this enzyme is no longer going to function. The other option is that the inhibitor doesn't bind to the active site. It binds somewhere else. But in binding somewhere else, it messes up the shape of the enzyme molecule. Even though it's not binding to the active site directly, that has somehow messed up the polarity of the molecule, and thus the molecule doesn't have its unique shape anymore. It is a deformed shape, and you can see in the lower right, with that deformed shape, that enzyme isn't going to work.